pleased to have Mike Miller. He's talking about Equivariant Instanton homology, and I will let him take it away.
Thank you, Dave, for having me. And I'll certainly stick around for a bit afterwards in case people want to talk. I've got the time. So first off, I'm mostly going to be doing, I hesitate to call it a chalk talk, but I'll mostly be writing as we go. I figured I'd write out the stuff that we all pretty much know by heart ahead of time so that we don't get too caught up in writing it out repeatedly. So I want to talk to you today about functoriality and invariance of equivariant instanton homology and what the relationship to Caston and Walker invariants are, or at least what it feels like. Everything I talk about today is work in progress with Ali Daimi. So first, I want to remind you of what you know about the instanton and framed instanton chain complex of integer homology spheres. Move on to what this should look like for rational homology spheres, the appropriate sort of direct generalization. And then how we deal with the traditional bugbear of the field, equivariant transversality, or rather the lack of. What this buys us and what we expect this buys us that we can't quite promise yet. So to go through that history, attached to an integer homology sphere, you can cook up the configuration space of SU2 connections on the trivial bundle. There's a million variations on this. You could work with SO3 connections on various other bundles. This changes things slightly when you work with rational homology spheres, but I'm just going to pretend we're working with the trivial bundle all throughout today. You have the configuration space of SU2 connections on your manifold. You've got a functional, the Chern-Simons functional. Its critical points are the flat connections on Y. Its flow lines are the instantons on Y, the anti-self-dual connections. And sort of at the point that starts a lot of our field, Floer packages this into a complex, a chain complex, whose homology is an invariant of that integer homology sphere. It doesn't depend on all the auxiliary data I'm hiding under the rug, like metric and perturbation. This complex has generators, those irreducible flat connections, and the differential counts the index 1 flow lines, imitating the Morse homology of this infinite dimensional configuration space. The resulting homology groups are functorial under cobordism, and one quickly gets inspired to try to generalize this, both out of intrinsic interest for three manifolds and for the sake of calculating things like Donaldson invariance by cutting up manifolds into pieces. More can be said, though, especially if you're interested in calculating Donaldson invariance by cutting up a manifold into pieces, computing on each piece, and so on. The Floer's original complex isn't quite the invariant you want to look at, with the issue coming from factorization through the trivial connection. So in his book, the small blue book, Donaldson defines a complex which does capture all the relevant information, called the frame, well, which I would call the framed instanton complex, Ci tilde. It's built out of two copies of the original complex Ci star and an extra term in degree 0. You think of these two copies of Ci star of Y as contributing the homology of a copy of SO3 for each irreducible flat connection. And you think of this last term, the Q there, as contributing the homology of a point for that trivial connection that we've been ignoring so far. This complex has a differential which includes both the information of Floer's original complex, counting the irreducible flow lines, as well as counting flow lines with prescribed holonomy. So we have a term going from this portion to this portion, counting flow lines of index 4, whose holonomy is minus the identity. We have a portion going from the irreducible part to the fully reducible part, counting instantons. And we have a part from here to here, counting instantons coming from the trivial connection to an irreducible connection. Donaldson talks about a certain structure on this, which is almost precisely, not quite, but almost precisely, the structure of a DG module over the alternating algebra on one generator in degree 3. That is a very silly way of saying I can kill off this last term and send this term isomorphically to this term, and that preserves the differential. Preserves the differential up to a sign, which you see in the expression there. If you want to see what a picture of this looks like, if you write down the framed complex for the Poincare homology sphere, you have two irreducibles, one in degree 1 and one in degree 5, contributing these two copies of the homology of S3, the trivial connection in degree 0, and your differential gives you a 1 down here coming from that D1 term, and a map from the bottom part of the irreducible in degree 5 to the top part of the irreducible in degree 1, coming from that U map, counting instantons with prescribed holonomy. This is, just as the original instanton complex is an attempt to model the Morse homology of the configuration space By, this is an attempt to model the Morse bot homology of the framed configuration space. Instead of taking the space of connections modulo gauge, you take the space of connections with a prescribed framing of your bundle at a base point, modulo gauge. This is now an honest manifold with an action of SO3, SU2 mod at center. And what were previously critical points in the configuration space become critical orbits in the framed configuration space. What used to be an irreducible flat connection gave us an orbit homeomorphic to SO3. This doesn't appear in the integer homology sphere case, but we'll see later that if you have a U1 reducible and a rational homology sphere, this contributes an orbit diffeomorphic to S2 in the framed configuration space, whereas central flat connections contribute orbits which are just points. From the equivariant, homotopy type of this complex wide tilde CI, you can recover a lot of interesting things. First off, you can recover the original complex of Donaldson again by looking at the image of this element chi3. That's just this term here. That's just the top degree elements. You don't pay attention to the trivial connection. You don't pay attention to the holonomy map. You can define the equivariant or Borel and co-Borel homologies and fit them into an exact triangle, like I've written here. You can define Froishov's H invariant from this data and define the reduced instanton homology of this 3-manifold Y, of this integer homology sphere Y. So what I'd like to talk about is how to generalize this to the case of rational homology spheres. Both what does the complex look like, what structure do you get from it, and what survives, what actual invariance of the rational homology sphere do you get? And actually, I'm going to go one slide back for have a little off by one error on my slides for a moment here. The key takeaways, I think, from this complex, the way I've written it here, is that the framed complex of a rational homology sphere should incorporate something like the chains or the homology of each critical orbit in its definition as a summand over here. The differential should include information both about instantons from and to reducibles, but also include information about the holonomy maps of your instantons and count instantons with prescribed holonomy. Not a takeaway from the previous observation, but a point to be made is that I wrote everything over here with rational coefficients. If you want to define an analogous model of this for non-rational coefficients, you probably don't want to use the homology of alpha because the integer homology of SO3 is not a free module over Z, and we're very used to working with free chain complexes. So in that point A up here, we really want to be working with some kind of chains on alpha, not the homology of alpha. So what I want to talk about now is an analogous model for the framed instanton complex for rational homology spheres. I'm going to, yeah. And here is where I'll start going live. I've talked before about a model for this complex, which is uncountable dimensional. You take a sum of something like the singular chains on all of the different orbits, and then have a differential which somehow encodes the push-pull map, apologies. There's something that encodes pullback and push forward by your moduli spaces running from alpha to beta. This is a very large and complicated complex. So what I will be, this is a large and complicated complex. So I'd like to give a description of something a little bit more concrete. Before I'll tell you the complex, I'm going to tell you the building blocks in this complex. Before, our relevant DG algebra was the homology of SO3, and the relevant building blocks were the homologies of the orbits. Our DG algebra is slightly more complicated. I'll give a formula and then a description, and then a picture. It's a four-dimensional algebra, dimension in the sense of rank over Z. It has a generator in each degree 0, 1, and 3. Chi1 squares to 0. Oops, wrote this very wrong. The differential d chi2 is 2 chi1. And that top element chi3 is both chi1, chi2, and minus chi2, chi1. This is precisely the cellular chain algebra of a particular cellular structure on SO3, so that multiplication is a cellular map. The way I usually picture this is 3 dots stacked on top of each other, or draw a little arrow to represent the differential on this. Chi1 takes the bottom dot to the second dot, the third dot to the fourth dot, but kills the second dot. Chi2 jumps you up 2 whenever you can. Oops. Our building blocks, by comparison, are meant to look like the cellular chain complexes of SO3, S2, and the point as modules over this cellular chain complex. We have, this algebra as a module over itself, giving us something which should represent the cellular chains on SO3. We have what you get when you quotient by chi1, which looks like something in degree 0, something in degree 2, with chi2 connecting them. And you have the rather uninteresting module M point, which is just a single generator in bottom degree. Chi1 and Chi2 and Chi3 all act trivially. The identity element acts as the identity as it should. The instanton chain complex is built out of these building blocks. One of these for each critical orbit. One of the first for irreducible critical orbits, one of the second for abelian but not central critical orbits, and the last one for those central critical orbits. So we set y tilde ci of y where here y is, say, a rational homology sphere. We say that the framed instanton complex.
I'm sorry, Mike, can I interrupt? Is chi2 nilpotent?
Sorry, I didn't write any of the relations that involve things beyond degree 3 because everything above degree 3 is identically 0. So chi2 squared is 0, chi2, chi3 is 0,
okay.
and so on.
Got it. Thanks.
Yeah, for sure. Thanks for asking. So the framed instanton chain complex is, as I was saying a moment ago, we add a copy of that first module for each irreducible. I write those angle brackets to label the elements. We add a module of the second type for each U1 reducible, and a module of the last type for each central flat connection. Oops. Sorry, one moment here. And our differential we can use the canonical bases of these modules. This module as a basis given by the 4 dots I just drew for you. This module as a basis given by those 2 dots, 1 and chi2. And this module has a basis just in terms of this dot down here. We can write a chain complex for this, we can write a differential for this chain complex, breaking this up into a block matrix. We have a portion going just from the irreducibles to themselves. I'm not going to define most of these terms, but I'll give a sense of what they're supposed to be doing in just a moment. We have a portion going from the reducibles to the, from the irreducibles to the U1 reducibles. And a component going from the irreducibles to the central flat connections. There's no component running from the reducibles to themselves. And from the irreducibles back to the reducibles, we have a component now. So far, I've just written down a bunch of meaningless symbols. To try to express the point here, I want to go back to that key takeaway I mentioned a moment ago. The differential should include information not just about the index 1 flow lines, but also higher index flow lines with specified holonomy. If I look just at this top left block, for instance, this term U3 runs from the bottom degree element to the top degree element, somehow representing taking a single framing and sending it to an SO3's worth of framings. We measure when that happens by counting in the previous, in the case of integer homology spheres, we counted something like that by looking at flow lines with holonomy equal to a specific value in SU2. The way we'll do this for all of these other terms is similar. Instead of saying that the holonomy takes on a specific value, we demand it lies in a specific cell in a certain cellular decomposition of SO3 or of S2 or of, well, or the uninteresting cellular decomposition of the point. Sorry about that. Just to give a specific example here, if you look at the instantons running from alpha to beta, with holonomy, let me write this down below. With holonomy in JS1, that gives you this term U2. The places we prescribe the holonomy lie in a certain dual cell decomposition to the cell decomposition we started with. Going through the details, too much of the details here can get a little bit tedious. So I'm going to sort of just leave it at that. The various terms in the differential here count instantons, and the more the index increases, the more specified the holonomy is of the instantons that we're counting. So before going on to what's new, what we can do with this phrasing, with this complex, I want to remind you what I already know from from my previous work, and sort of where this leads to from there.
So
Before
you go on,
mm-hmm.
So in all this, this is the way you're presenting it is that it's as if everything's already, all these flat connections are non-degenerate in some appropriate sense. So are you going to tell us something about how that's to be achieved, or?
So in my original paper, I was able to show that you can always achieve that, and I was about to state that in the next theorem. I'm being a little sloppy here. Really, I should have said to every integer homology, every rational homology sphere Y, and regular perturbation, which always exists, et cetera, et cetera, et cetera. And that'll pop in the following statement.
Okay, thanks.
And just one more thing before I write this down. I'm recently married, so my initials have changed, and I promise I'm not just being egotistical here. Attached to every integer homology sphere with a choice of regular perturbation, meaning that all critical points are cut out non-degenerately, all moduli spaces of flow lines are cut out non-degenerately. This always exists for a 3-manifold and the moduli space of instantons on the cylinder. Things get a lot more subtle for general cobordisms. We can attach a module over what I did then was all chains on SO3 called y tilde of y tilde CI of y pi. Which is functorial under a relatively weak class of cobordisms. Roughly, this, I'll actually describe the cobordisms in just a moment because I need to say a little bit more to describe exactly what this construction is invariant under. Because what today is about is how to improve just a little bit, how to get it to be invariant under more than what I'm saying. We have a module, y tilde ci of y pi, which is functorial under a relatively weak class of cobordisms. To describe what it's invariant under, let me first describe the auxiliary data that this is ultimately going to depend on. Much less than a perturbation, but still much more than we would like. Attached to every rational homology sphere is a set of U1 flat connections. If you like, you can think of this as the first homology minus the tube torsion, quotiented by plus or minus 1. And to each regular perturbation pi is attached a function, which I write sigma pi assigning an integer to every U1 flat connection. Somehow this is supposed to measure the number of eigenvalues that are made positive as you pass from the trivial perturbation to your chosen regular perturbation. You're recording what's happening at the index at these reducible flat connections. And the statement is that, oops, that's not true. It's not that the complex only depends on that, but rather that the equivariant homotopy type of our complex only depends on the underlying rational homology sphere Y and this function. It doesn't otherwise depend on the perturbation itself. And when I say it's functorial under a weak class of cobordisms earlier, these are roughly the cobordisms in which the signature decreases across the cobordism, or at least it doesn't increase more than the twisted signatures of the cobordism itself. On a cylinder, if you're trying to get a continuation map from Y with one perturbation to Y with another perturbation, what this says is if I name the set of functions on our set as SD of Y for signature data, then you have a cobordism map, an essentially unique up to equivariant homotopy cobordism map from Ci tilde with respect to one perturbation to Ci tilde with respect to another perturbation, precisely when the signature decreases across the cobordism. Your signature on the left side, your signature data on the left side is larger than your signature data on the right side.
Mike, can I ask a quick question?
Please.
Why are we seeing a torus when we're looking at the reducible flat connections? Are you modding out just by the identity component of the gauge group?
Say again, what torus?
So when I think of reducible of the moduli of U1 connections, I usually think of the Jacobian torus.
But we're working with rational homology spheres. So I mean, there's B1 is 0, so our torus is just a point for each of them.
Got it. Thanks.
Cool. That makes that torus makes the whole thing more subtle past the level of rational homology spheres, which is why we want to understand this comparatively simpler case first. So the other punchline of what I did then is that from this equivariant homotopy type, which is an invariant of something, but an invariant of less than we'd like it to be, and there's something notable about what exactly you can recover here. First off, you can recover or define the so-called equivariant instanton homologies, I plus, I minus, and I infinity, and the exact triangle relating them. A rather silly thing that you can recover is the homology of this chain complex I tilde. We expect that that's actually going to be a very uninteresting invariant, even though Ci tilde has a lot attached to it. But frighteningly, you can also recover what I might call the irreducible instanton homology. The homology of the complex you get by adding a Z for every irreducible flat connection and counting index 1 flow lines between these. This is extremely not an invariant of our rational homology sphere. There's there's two ways of thinking of this. First, there's a nice extended discussion at the end of Donaldson's book where he describes what happens as you try to construct a continuation map relating these things. And one of your irreducibles gets sort of sucked into the reducible that you're ignoring and completely vanishes. In fact, actually, let me hold off on saying the thing that I was about to say. But this is a little concerning. When I see this, I get a little freaked out because this is not an invariant of Y. Whereas I expect the other terms here to be invariants of Y. So the question is, what do I do now? The way I showed that these things were invariants of everything they're invariant of so far has been by constructing Coborda's equivariant chain maps both ways, showing that the composites are equivariantly homotopic to the identity. That literally cannot work here because that would prove that something is an invariant which isn't.
With the kind of weak cobordism you're considering, I mean, is that a property of the cobordism or a property of the cobordism with the perturbation data?
It's a property of the cobordism with perturbations attached to the three manifolds on the ends. Okay, so I mean, it doesn't rely on perturbations across the cobordism though? I mean, it does not. Okay. It's almost topological. It's topological plus the data of these signature data on the ends. Okay. It's really a statement about some twisted signatures over W not being too much larger or too much. I forget the sign right now. Not being too much something compared to the difference in those two signature datas. What do I want to say now? So I think first I'll tell you what the solution ends up being and then sketch a little bit about what the terms mean and how we construct the relevant maps involved. So far, I've been trying to construct equivariant homotopy equivalences between these complexes, but I don't actually need that much. If I have an A-equivariant quasi-isomorphism, it's an equivariant map which induces an isomorphism on the homologies of these chain complexes with an action of A. By a spectral sequence argument, necessarily, that map induces an isomorphism on all the equivariant homologies of these complexes as well. So if I'm trying to show that the Instanton homologies are so that the equivariant Instanton homologies are invariants of Y, I should be trying to prove that the maps I have on the left board here, these signature decreasing maps, are quasi-isomorphisms, instead of trying to prove something far too strong. The phrasing we end up getting is as follows. Let's see. If I have a given rational homology sphere Y with two adjacent signature data, adjacent meaning that there's no other signature datum strictly in between them, precisely they're equal for all of our U1 reducibles except for one, where the right side is just one larger. Oops. This allows us to focus our attention in on one reducible. It might be helpful in what follows to pretend that I'm working on a manifold with exactly one U1 reducible flat connection to begin with, something with homology Z mod 3, say. If you have adjacent signature data in this sense, there is a complex called the suspended complex, which I'll describe in a few minutes after stating the result. This is an SO3 module, which fits into a diagram where my top map here is the one promised by what I already know. I know that when signature data decreases across a cobordism, I get a chain map between these complexes. I'll call that lambda minus. I have a map S going from the complex Ci tilde to the suspended complex. And it's in that suspension map that we localize all of these problems about not being able to find equivariant homotopy equivalences. This map S is an equivariant quasi-isomorphism, but not a homotopy equivalence. I don't have a map right. There's no map that ought to be called lambda plus, but there is a map to the suspended complex, which maybe ought to be called lambda hat plus, and a map going the other way called lambda hat minus. Which are equivariantly homotopy inverse to one another. One of these maps is somehow a suspension of the original map we started with, and the other encodes information that we just couldn't have with the chain complexes Ci tilde themselves. Because that map S is an equivariant quasi-isomorphism, in fact, and lambda hat plus, lambda hat minus are equivariant quasi-isomorphisms. It follows, by 2 out of 3, if you have 2 maps which induce isomorphisms, so does a composite, you know what I mean by the 2 out of 3 property, even though I'm flubbing it here. It follows that map lambda minus induces an isomorphism between these framed instanton complexes and on all equivariant homology groups attached to them. So this statement is the claim that in fact the equivariant instanton homology of a rational homology sphere is an invariant of the rational homology sphere. It doesn't actually depend on the choice of signature data. But because we're invoking that S is a quasi-isomorphism and not a homotopy equivalence, that map lambda minus is simply not a homotopy equivalence. And, that map is simply not a homotopy equivalence. And that irreducible part, that irreducible instanton homology, is not an invariant of Y. With the time I have left, I'd like to talk a little bit about what this suspended complex is supposed to be, where the idea comes from. And the inspiration really comes from trying to understand the Casson-Walker invariant. When defining the Casson-Walker invariant, you end up doing something not too dissimilar from what I'm talking about here. You have a count of irreducible instantons, some contributions from the reducible instantons, and you check that when you change the index at one of these, sorry, I keep saying instantons, at one of these critical points, when you change the index at one of these reducible critical points, an irreducible pops out of it. In that description in the book by in Donaldson's book, whenever you tried to do your continuation map in which whenever you try to change an index at the reducible in your continuation map, something gets sucked into that reducible, or going the other way, something pops out of the reducible. The suspended complex should replace that term that module attached to rho naught with instead a new module including an irreducible and a reducible of lower index to compare to the lower index reducible over here in wide tilde CI on the left side. The picture I have for this is that I think of M sub S2 as looking like those 2 points. And the thing I want to replace this with, I usually draw as a copy of the irreducible topping out in the top degree of my reducible, whose differential encodes both the differential on the chains on SO3, as well as a relationship between this and the reducible of lower index. There's a natural map from the left side to the right side, which is an equivariant quasi-isomorphism. If you take the homology of this creature on the right side, you get the bottom few dots just disappear, the right dots disappear, that second to top dot disappears. All you're left with is the ones I started with on the left. But now it also receives a map. An equivariant map from that same module, the module of the S2, the cellular chain complex of S2, to those lower degree reducibles. When I look at this map lambda plus, what it wants to do, it wants to send this reducible rho minus to this reducible rho naught rather, to the same reducible on the right side, but it wants to send the top degree element to something in bottom degree. I say right side and left side, but my picture here is mirrored from what I was drawing over there. This term in the middle allows us to interpolate between these. There is no equivariant map from this expression over here to this expression over here. Like Ciprian asked earlier, chi squared is 0. So whereas chi2 of this, or chi2 of this should be 0 up here, I can't send it to something non-zero over here, where chi2 of this is not 0. This complex allows us to, what do I want to say? It just allows us to actually encode this map. One nice upshot of this is that we can very explicitly describe the relationship between the irreducible instanton homologies of these adjacent chambers in the space of perturbations. If sigma and sigma prime are adjacent, there is an exact triangle relating their irreducible instanton homologies. There's an extra term, a z in even degree, which fits into an exact triangle with these other two terms. And in particular, the Euler characteristic of I star sigma is the Euler characteristic of I star sigma prime plus 1. The plus 1 is contributed by this new irreducible I added that came from what was previously irreducible that didn't contribute to this irreducible complex whatsoever. This jump in the Euler characteristic suggests that the irreducible instanton homology should somehow categorify the irreducible count in the Kassin-Walker invariant. Its Euler characteristic jumps by exactly the amount that the irreducible count in the Kassin-Walker invariant changes whenever I change the index at irreducible. We expect, or suspect rather, that incorporating these suspensions as appropriate should allow us to construct an honest categorification of the Kassin-Walker invariant itself. By adding in these suspensions whenever we change between adjacent chambers, we should be able to counteract the jumps in the irreducible count, the fact that these are not invariants of Y. Now I've mostly been focusing on invariance here, and there was that functoriality in the title of the talk. So let me say a little bit about what we expect this to do for us. When I said earlier that this is functorial only under a, where is this? There we go. Only under a weak class of cobordisms. The issue was that the signatures on the two sides might not be far enough apart. I really want the signature to decrease, and to decrease a lot, much more than any twisted signatures on the cobordism itself. The fact that I can now change the signature data at these reducibles freely without changing my equivariant homologies the fact that we can choose the signature data freely should promote these four, should promote these four groups to functors under negative definite cobordisms. We have essentially two problems stopping us from defining cobordism maps in general. One of them is the equivariant transversality, or the index problem associated to each of the reducible flat connections on the cobordism. And one of them is the one associated to the trivial connection on a cobordism with trivial bundle. Whenever we're working, this allows us to resolve all the issues with our standard reducible flat connections. Sorry, I lost my train of thought there. The trivial connection still needs to be dealt with, and we haven't thought too hard about what the technology for that should be yet. The fact that I now have all these new cobordism maps and can prove the relevant composition relations between them. These new cobordism maps should give rise to a surgery exact triangle. When I wrote my thesis, there weren't enough maps to actually construct the relevant maps in said triangle, but we've resolved the relevant issues. We've resolved the relevant issues involved in the surgery triangle itself. Sorry about that.
Do you avoid surgeries that sort of give rise to positive B1, or do you have something to put there?
Yeah, so I'm being a little sloppy in the phrasing here. I've only been talking about rational homology spheres with you, but unless I'm being totally remiss in my thought process, the ones you're thinking of, oh sure, I'm talking about +1 surgery right now, I should say specifically. In that triangle, you do get something with positive B1, but it has an admissible bundle over it. I've been not talking about the admissible bundle part of the story here, but that all works fine. Is that what you were looking for?
Yeah, I just wanted to make sure that you just put that there for the sort of zero surgery, and not something more exotic.
I gotcha. The fact that we have this invariance result, that these equivariant instanton homologies are honest invariants of Y, should lead to Freushoff invariance for rational homology spheres, especially because of the very explicit way we can see how these adjacent chambers are related. We can see very concretely what that does at the level of, say, I infinity, which is where the Freushoff invariants sort of live. The small model I've been presenting here is much more amenable to proving the connected sum theorem than the large model I've talked about before. And in particular, applying that to the 3 torus. We expect to be able to recover the equivariant the framed instanton homology of Y by something like the homology of Ci tilde with a perturbed differential. We don't at all expect that I tilde and I sharp are isomorphic, but we do expect that a slight perturbation to the differential gives rise to a complex computing I sharp for rational homology spheres. There's surely plenty more to explore here that I haven't talked on or that I haven't talked about or written down, but I think I should stop here for now. Thank you for your time. That I ended on a high note there, but that was supposed to be thank you for your time.
Do we have any questions?
You mentioned categorifying the Caston-Walker invariant, but isn't that a rational number?
Yeah, so I mean, you have to, I should say something like the cardinality of, I mean, I always forget the precise denominator involved here. But the jumps you see here are exactly what you get when you multiply the Casson-Walker invariant by like 12 times the cardinality of H1 or something like that. The actual honest categorification of this, I'm not quite sure what to do with that yet. The irreducible count seems to be precisely corresponding to this CI star. And I have some ideas about how to adjust for the irreducible count, but I don't quite know how the various other axioms of the Casson-Walker invariant should categorify. So for instance, the surgery formula for the Casson-Walker invariant, I don't know, I don't have a prediction about what that would be in terms of the right kind of instanton complex.
The Casson-Walker invariant includes a correction term from just Chern-Simons invariance of the flat connections, which is not part of the story that you're telling. I mean, it doesn't.
I think, Tom, you're talking about SU3 Casson invariant.
What?
You're talking about SU3 Casson invariant. You mean the value of the Chern-Simons functional?
I see. Yeah, sorry. Yeah.
Got it. Yeah, I have nothing interesting to say about SU3.
Counter term, right.
So Mike, you mentioned this complex for SO3 that was invariant under multiplication. Can you say a bit more? Can you say what that is?
Yeah, I really like the geometry of this thing. So it's great to have an excuse to talk a little bit about that. The particular, let's see. The first two terms are easy to guess. Your identity element should be your generator in C0. SO2 inside SO3 should be the generator in degree 2. If you now think of this, the generator in degree 1. If you now think of this as being, say, the 3 ball with, if you think of this as, I wish I'd written this down next to me beforehand. But the point is that the next term here should be a D2 corresponding to, I mean, I guess the real answer is I'm forgetting the exact term here precisely. There's a nice formula that Ali wrote down for SU2, but I don't have it written down in front of me. The point is the second term here is it's a 2-cell which bounds twice this copy of SO2. It should correspond to the set of rotations, which, oh, right. This is, sorry, I'm remembering better now. This is sort of like a copy of RP2 sitting inside of SO3, thinking of this as the boundary of that 3 ball. This is the set of all rotations by 180 degrees around some axis. But I can't think of that as being a cell in any honest sense. So rather I take a D2, which runs twice around RP, whose boundary runs twice around RP1, sitting inside of RP2. And that RP1 sitting inside of RP2 is homologous to SO2. I guess the answer is no, I don't have as good an answer as I'd like for you. I had this written down at some point, but not directly in front of me right now.
That's fine. That's kind of the next.
I'll send you an email when I get a chance.
And if you wanted to do the S1 case, you would just take the identity and then all of S1.
Yeah, if you're thinking in general about when do these exist and how do you construct them, that's a great question. And if you ask for just a little bit more, it's an extremely open question. People don't really talk about CW groups very often. Sometimes they ask that inversion is cellular as well as multiplication being cellular. I know extremely few examples in the literature of constructions of CW groups. I know a CW structure on pin2 that you can find in some papers by Matt Stoff-Reagan. I know a CW structure on S1, SO3, S3. I probably know one on U of 2 if I fiddle a little bit, but past that, I don't really know any interesting examples. So I think it's hard to actually construct these cellular models and to do anything useful with them.
Okay, thanks.
It's kind of lucky that SO3 is small enough that I have a concrete handle on the geometry there, or at least I claim I do. It's not super visible on the slide I just wrote on the right.
Mike, sorry, silly question. So if you apply this same technology to say an irrational homology sphere to the Syrey-Witten equations, then like you get like some sort of equivariant monopole Slur groups, and would they like in any obvious way be isomorphic to the ones that you get like if you use like the blow up construction, or you think
whenever I'm asked this, I say, yeah, I would guess that's true, but I've never written down enough to actually convince myself that it's true. I feel like that's going to require a significant chunk of time to be more certain than I am. So I'm going to say, yeah, sure, probably, and leave it at that.
Okay.
I had a question about the suspensions.
Please.
Can you go back a bit to the slide? Yeah, so I was just wondering, it seems to me kind of like you're doing some sort of like cofibrant replacement in a sense. Is there a way to make that formal? Like
I only thought about this a little bit. If you were taking all the machinery of algebraic topology. Okay, let me answer your question first. No, I don't think that this is a cofibrant replacement. This is just enough of a cofibrant, it shouldn't be cofibrant in any sense. Cofibrant things should probably be built out of copies of the free module over SO3. This is just free enough to construct a map that I didn't know how to construct before. It's like doing as little cofibrant replacement as you possibly can to construct what you want to construct. There's a similar thing where I could have suspended on the left side instead, and lambda plus hat would have been a map going up and to the right instead. That looks a little bit more like cofibrant replacement, because here I've taken, when one does some cofibrant replacement, often it's something like a bar-like construction where you're just adding more and more terms to a resolution. The extra term you would add on the left side instead looks like something like this, where you're adding more and more terms. Actually, no, never mind. Strike this last comment. Basically, no, I don't think that it's an honest cofibrant replacement, but that's a good idea of what's going on. It's something like that.
Okay, cool. It's like a quasi cofibrant replacement.
Yeah. A lot of this is designed to use as few explicit generators as we can. So we didn't want to choose some gigantic replacement here.
Okay, I dig it. Thanks.
It also, just to butt in one more moment, it also fits with the geometry of the moduli spaces involved. Unfortunately, because of time, I can't really talk about what the moduli spaces that go into this cobordism map are. But when you start to look at the relations between them, you want to say, okay, there should be an extra term to capture information about factorizations through this bad reducible crossing that. And these two terms here are places to hold the information of those factorizations.
Okay, cool. Thank you.
For sure.
Hey Mike, I'm just a little confused about this map that you have on the right, like if I look on the homology of these complexes, just regular homology, the bottom term on the right goes to something that is trivial on the in the middle, right?
Right. So the thing you should be thinking of here is I've drawn this a little bit poorly to compare to the picture on the left. Let me draw these on the right sides to compare to the picture on the left. You normally have your rho naught on the left side of index to left than it is on the right side. I'll write rho naught minus and rho naught plus to distinguish them. What you want to say is that is multiple, it sends that top degree to twice the bottom degree on the right, and it sends the bottom degree to 0. You want to say something like your cobordism map cuts down by a section of a certain complex line bundle over rho naught, a complex line bundle of first Chern class 2. And this is very firmly not equivariant, cutting down by a section of a line bundle over S2. Correspondingly, the map I've written down here is not an equivariant map. What I want to do is stick something in the middle so that it does this on homology. Even if not quite. Oh, yeah, that's fine, I think. Okay, gonna try not to confuse myself too much more right now. So the bottom degree element does get sent to something which is 0 in the homology of this term. That doesn't tell you that it's 0, that even the differential of that thing is 0 in the chain complex Ci tilde, because there's maps coming out of these bottom two terms going somewhere else. There's information being recorded by this bottom degree element still, even though if I'm just looking at these specific terms in the chain complex, it doesn't look too interesting. And then the top degree element gets sent to something which is homologous to twice this thing over here. So you might be suspicious here, like I was for a bit, because you might say, okay, well, if it does that on homology, it still can't possibly be equivariant. But the issue is that chi2 is not a cycle in the homology, in the chains on SO3. So you don't expect multiplication by chi2 to induce a map on homology. The fact that this is not chi2 equivariant on homology doesn't mean anything, because there's not a chi2 map on homology. I'm not sure if I'm pointing at what you're looking for here, though.
Michael, I think it would be helpful if you kind of, I mean, there's a very clear picture where that comes from, right? Like you had the tangent bundle of S2, and you imagine that your Morse function is just, it's equivariant, so it's some positive definite form on the tangent fibers, and then you perturb it so it suddenly has a circle of critical points on each fiber, giving you a two-sphere and an SO3, and you're just recording in an equivariant way how that complex changes.
That's a very good description, I think. It's the thing going on in that last chapter of Simon's book, but done over S2 instead of just in a single complex fiber.
Yeah.
If you want to think about cellular chains here, you start thinking about like something like locally finite cellular chains. But this top term is the whole of TS2. This term down here is just a base point inside of the 0 section. This term up here is the 0 section of TS2. And these terms are certain parts of, like certain non-compact parts of TS2. This is a fiber. This is array in EX. And this term, there's not really a good geometric description of. It's like what happens.
That's not the picture I had in mind, actually. I mean, that may be a good picture for
Sure.
you, but that's not quite the picture I had in mind for what you're doing. Maybe you're doing something else then.
No, you're right. I started writing down a slightly different picture in case that was also helpful. I wasn't sure that I could do your picture justice without having something written, without thinking about it a little more carefully ahead of time. I would hesitate I hesitate just because I haven't worked that out by hand in front of me already. But if you want, Piotr, I can email you that description.
That would be wonderful.
Sure.
Yeah.